Okay, so in this episode, we're gonna study CMFR, continuously mixed flow reactor with first order reaction in both steady and unsteady. So steady state is actually a special case of unsteady. So if you solve unsteady problem, then you actually solve everything. So you have a reactor like this, and then your inlet concentration is C0, and with the flow rate Q, then your going out flow rate is also Q here. Otherwise, your water level is changing, which is not what we want. And CT, that is effluent concentration. And V is the volume of the water or solution, which is technically less than volume of the tank. So we could think about the mass balance. In other words, your accumulation should be equal to in minus out plus reaction. So reaction could increase or could decrease the concentration. So accumulation is how fast your concentration is changing times the volume. Okay, so this C is milligrams per liter, and then volume dimension is liter, and then you have time. So ending unit is milligrams per time. How fast this mass is changing with respect to time within this reactor of volume V. Okay, so let me clear it. Then incoming mass flow rate is Q with the inlet concentration C naught, and C out is same flow rate and concentration C. So this C and that one is actually same because we think that within this reactor, mixing is instantaneous. Then you have reaction. So reaction, we will use a first order, which is negative Kc. Okay, and but this negative Kc, that is mass per or concentration. So that one is actually the concentration per unit time. So to make it equal to other three, you need to multiply volume V. Now we divide both sides with the water volume to have dc over dt equals to Q over volume C naught C minus Kc. That we know that we define tau hydraulic retention time as volume divided by Q. So we could rewrite this as C naught over tau minus C over tau minus Kc. So we can group terms with the concentration C. So it is C naught over tau minus 1 over tau plus Kc. So just for simplicity, that we will just let this one equals to pk. So the governing equation that we actually need to solve is dc over dt plus kc equals to c naught over tau. Okay, then we'll say C0 is actually initial concentration. So initially this tank has initial concentration of C naught, and then this inlet concentration is coming in, and after a certain time that effluent concentration would be given with respect to time. So let's just try to solve this one. Okay, so here we have, just gonna write down a vertical line. So here the covering equation is dc over dt plus kc equals to c naught over tau. So this term should be simplified, and this technique is what we call the integral factor that you need to memorize. If you calculate c exponential kt, then you have dc over dt exponential remains. If you differentiate exponential, then you have k coming out, c exponential kt. Now um, if you multiply both sides exponential negative kt, then this term disappears. So technically we prove that this term equals to that one. Okay, therefore on the right hand side this should be equals to c naught over tau. Now you multiply exponential kt both sides to have dc c over dt c exponential kt equals to c naught over tau exponential kt. So now you could actually integrate both sides by multiplying dt, t from 0 to time t. So here your left hand side is c exponential kt, t is from 0 to t. And then your right hand side, constant coming out of integral, and then you have exponential k, let's say t prime, dt prime, and from t prime 0 to t. So left hand side should be c t exponential kt minus c at t equals 0 times 1 equals to c naught over tau. If you integrate exponential kt, then k exponential kt prime, t prime is from 0 to time t. So if you, and then your left and right hand side would be c naught over tau, k exponential kt minus 1. So if you multiply the exponential negative kt, then you get ct equals to c0 exponential negative kt plus c naught tau k 1 minus exponential negative kt. Okay, so this one is actually the solution, final solution. And then you need to make sure that this one satisfy all the conditions that we actually used. At t equals 0, and you say this term c naught times 1 plus c over tau k 1 minus 1. So equals to c0. So this condition is used in here and also indicated here. So initial condition is satisfied. Okay. Then there are another one that what if you have time is quite long. So in other words, let's just delete this one quickly because we already wrote it down. If t goes to infinity, in other words, k times t is much greater than 1, then you could say c t goes to infinity. You can just denote this as c sub infinity equals to initial concentration times 0, because this term is very small, plus c0 over tau k 1 minus 0. So if t is very, very large, or t is much, much greater than 1 over k, then effect of initial concentration is negligible. And then this term is also 0. So it is C0 over tau k. And recall that k is this guy, C0 over 1 plus k tau. So this is actually the concentration in steady state. Okay. Our goal is to decrease this steady state concentration as much as possible, because that is a contamination uh, concentration or pollutant. There is only two way, because you have C naught, the inlet concentration is almost given, then you don't change. So way to decrease this one is by increasing k times tau. If you increase k times tau, then you can decrease the effluent concentration in steady state. How? K is a reaction constant, right? First order. So you can not change it too much. One way is that you could change the chemicals that can react better, but that is like big task. And easiest way is increasing tau, hydrolytic retention time. And you know that tau was given as solution volume divided by flow rate. So if your effluent concentration is relatively high, then the only way, or easiest way, is slow down Q, then tau, hydrolytic retention time, increases, and then your denominator increases, and so effluent concentration decreases. Okay, that's it for CMFR reverse reaction in unsteady state. So you actually have a couple of parameters. Those are initial concentration, where when reaction start, then what is the leftover concentration. But this one is not important. Usually it is same order or less than the inlet concentration. And then in steady state, this term disappears, and k times tau times bk, that is 1 plus k tau. And if we could ever control the product of reaction constant k and hydrolytic retention time tau, that is the way you could control this one. Note that all of these derivations came out of this governing equation, and it is only for the first order reaction. You could put the zeroth order, second order, or arbitrary, but if it's not nonlinear, if it is nonlinear, that is very hard to solve. Therefore, it is the linear reaction or forced reaction is often used, and in environmental engineering, the most of reactions are linear because their concentration is very low. Okay, that's it for today, and I hope you remember how to uh, derive this effluent concentration with respect to time, which is general solution, and how to check the validity of this equation by confirming that initial concentration is satisfied. And then the steady state concentration is one thing that we could actually uh, get nearly by solving this governing equation exactly. So this is how the applied mathematics is used for one of the environmental engineering applications. Okay, that's it, and I hope you remember three things: general solution, initial condition met, and then the steady state concentration.